Here we go, knocking out algorithms. So the primary purpose of this video series is going to be for analyzing not just algorithms, but also primarily pieces that are going to be utilized not just in computer science, but also for interviews. And we're going to be starting off with something called the Big O. So really quickly, and we're going to be doing this all in the Jupyter Notebook. Primarily because it's not that difficult enough that we have to use PyCharm, and it's also a little bit cleaner looking. So why analyze algorithms in the first place? So an algorithm, don't get nervous by the word, it's just a procedure or formula for solving a problem. Some of them are so useful that we've given them names like merge sort or bubble sort, etc. And then one of the important things we're going to come across, you're going to see very quickly, is how can we compare the algorithms to know which is better? And by better, it's going to be a relative term to the task at hand, but typically there's going to be two avenues for analyzing if an algorithm is better than another, and that's going to be either by speed, time of completion, and that's going to go into its scalability, and also memory, its size allotment, and its requirements, and so forth. So really quick, let's jump in. So in this first segment of code, I said, imagine about this function. This is just defining a function called sum of one. It's taking one argument, n. So then we have final sum equals 0. So we have an object final sum, and we're giving the assignment of 0, and it says for x in range n plus 1. So we just have a for loop here. Range is going to be whatever we define it for in terms of the n. So n plus 1 equals final sum plus x. And then we're returning the final sum. So I'm just going to shift enter so that it actually loads into the Jupyter Notebook. And then I have here sum 1, and I'm calling 5 as the argument. And you'll see that it prints out 15. So what this did was, with the object having the argument of 5, and the formula, essentially the algorithm for this, was for x in range. So for each number in range, n plus 1, n was 5. So in 6, you have to remember for range, we started at 0, so we had to add that 1 if we wanted to really get 5 actual numbers. So because 0 is not going to have any implication for addition. And the final sum was starting at 0. So if we did 5 times 4, we're going to have 9. 9 plus 3 is 12. 12 plus 2 is 14. 14 plus 1 is 15. So of course we got the answer to be 15, so that's appropriate. So let's see what this is all going towards anyway. So again, this is a function that we've created defining a sum of 1, and we got a result of 15 when n equals 5. We're going to go down here now for this point, and let's assume that you gave me this function. You called it sum2, also taking only one argument of n. And you, instead of doing a for loop, you're just returning n times n plus 1 divided by 2. And let's see what we get. I'm going to shift enter through that as well. And same argument of 5. And we also get 15. Same exact function. If you actually did this math by hand, of course, PEMDAS is going to hold place, so parentheses are always going to be first. So you would have had 5 plus 1, which is going to be 6. 6 times 5 is 30. 30 divided by 2 is going to be 15. So what's the point of this? Essentially, we got the same answer with two very different functions. That's essentially that's the point of this. So this is my function I created, and this is the one that you created, both getting the same result. So function 1 is, someone's going to complain about that, right? F you. So function of sum 1, it's using a for loop to iteratively add across our range of plus 1. So here's our for loop, and we're just iterating over the range that was dictated by the input n. And it's adding across that range. Number 2 is simply just taking advantage of a formula. It's a formula base to solve a problem. Both of these are technically algorithms, because remember the algorithm is just a procedure or a formula for solving a problem. So we're solving a problem, and here we're solving a problem. This is just more formula based, and this is an iterative for loop that we're running. So now the question is going to come, how do we compare them? How do we determine whose function is better, mine or yours? And that's going to become relative to what it is we're trying to determine defines as better. So we have to objectively be able to compare them. And the two avenues I mentioned before that we can do that for is memory, which is space allocation within the computer, or the time to run. How much time is it going to take to actually run that software? So we're going to use built-in magic commands in the Jupyter Notebook. Sometimes I might call it IPython. That's the old connotation, because back then it was just Python, and now it's multiple languages, so they call it Jupyter Notebook. So first off, this is a magic command using the percent sign, time it, and I'm saying I want you to time it for the sum of one function with an n of 100. So I'm going to shift enter that, and right now what it's doing that for loop. So there we go. We got 100,000 loops, best of 3.74 microseconds per loop. And then I'm going to do the same magic time it sum2 with 100 as the input. We'll get to her in a moment. And then, oh, it's doing the computation now. It took a second there. Depending on your computer, it's going to determine if it happens faster or slower. So for the same n of 100, which we know that they're going to give me the same answer, and you can ignore this for right now, it's just talking about caching. Best of 344, but now this is nanoseconds. So, and I put down here, just for those who may not know, micro, which is up top here, is 10 to the minus 6. Nano is 10 to the minus 9. So that means nano is a smaller number by a factor of 3. And so this is faster. So in the two different functions we had, function of sum 1 and function of sum 2, for the same n, my algorithm, your algorithm was a function, was much, much faster. You were on nanoseconds, I was on microseconds for time of completion. But now that's not necessarily the end-all be-all, because that's the time of completion on my computer. Your computer, the time of completion might be faster or slower. Now, of course, granted, we're talking micro and nanoseconds. That difference can get very large, and we have much larger inputs to deal with. And some systems will be faster and slower, but at the end of the day, regardless, for loops are always going to be slower. And that's why we try to avoid them, and especially machine learning, artificial intelligence. So now that we have that, I have your smallest number is obviously faster, we know that. So we can't rely on just time to run, because again, all computers are different. Hardware is going to be different. Some are faster than others. We want this to be hardware independent. And that's one of the big takeaways, because as you know, hardware is constantly changing. So how can we objectively determine if one function is faster or slower, or rather is better or worse than another function, if we can't use the time parameter per se because of the objective nature of different computers? Well, that's where the big O comes in. And that's why I had her here. I mean, it's not this big O, but that is just as important. So the big O is a way that we can objectively compare the efficiency of those two algorithms. So we're going to compare the number of assignments of each algorithm. Now there's some key phrases here that we're going to run through, and this is what I want you to be cognizant of. So we're going to compare the number of assignments that each algorithm makes or has to undergo. So for the original sum1 function, I'm going to read this and I'll go back up to it and show you what I mean. The original sum1 function will create an assignment n plus 1 times. We can see this from the range-based function. This means it will assign the final sum variable n plus 1 times. We can then say for that problem of n size, in this case just a number n, this function will take 1 plus n steps, and this 1's going to become meaningless. So going back up to function number 1, or sum1, what it's saying here is that the allocation that this is going to require in terms of an assignment, it's only the assignment is this. So if my n is 1, it's going to have two assignments. It's going to have the assignment of 1 and then the assignment of 0, because again we're dealing with indexing of 0 and it's ranging. If my n is 3, then we're going to have 4. It's going to be the assignment's going to still be n plus 1, because whatever the n's going to be, it's going to be linear is the point. That's what we're going to be looking at here. But there's only one assignment that's necessarily going on within this. And our final first assignment is 0, and then that assignment's going to keep changing based on an order of n. The n notation allows us to compare the solutions and algorithms relative to the size of the problem. So since sum 110 and sum 1 of 100,000 would take very different times to run by using the same algorithm, we can also note that n grows very large. The plus 1 doesn't have much effect. That's what I was referring before. Some of these constant numbers, essentially, when you start to get to numbers like infinity, or if you're familiar with calculus, when we get to limits, the constant numbers just drop off. They no longer have a real effect on the ultimate coding, and you'll see that in just a minute. So how can we still quantify this? How can we still compare the functions? And that's where big O notation comes in. It's describing how quickly the runtime will grow relative to the input as the input gets arbitrarily large. And again, this is how we're going to measure one algorithm over another, or even one, different coding aspects like using NumPy in an instance, so it can be a heck of a lot faster than if you're using a built-in list sequence in Python, using data frames instead, also utilizing pandas. So it's all, the big O, what I want you to put in your head is how well can it scale as the data increases, because big O has a lot to do with scaling. And that scaling can either be in time or it can be in memory. So we're comparing how quickly the runtime is going to grow, not the exact runtimes, since those are going to
depend on the hardware. So at least this way I can know it doesn't matter the system. If I have two different algorithms, I can tell you that one algorithm is going to have some element of time and this other algorithm is going to have a comparatively different relative amount of time. Regardless of the hardware, one's going to be faster than the other if I can see the code and I do the big O notation. So as the n gets arbitrarily large, we're only worried about the terms that will grow the fastest as n gets large. So essentially, if you're looking at an algorithm and if you're trying to, which we're going to get down to in just a second, you're trying to determine which element in that code is the driving factor, which one's going to actually impose the limiting behavior on the execution of that code. Well, that's going to be your big O, and everything else is essentially going to drop off. And in math, that's this idea is called asymptotic analysis, which is just describing limiting behavior. So it's kind of looking at a whole picture. So we're going to get to this guy in a second. So asymptotic analysis is looking at this return here and pretty much saying, who's the limiting factor in here? Who's going to limit what my n is going to be able to do? Which one of these guys is going to mess with scaling the most, or have the most impact or the least impact on scaling, and then you can go from there. So again, which part of the algorithm has the greatest effect on the final answer? Which part of the algo is the real bottleneck? Which is the limiting factor? As for the syntax, someone can be said to be, this is the notation here. So say this is a big O of n, since its runtime grows linearly with input size. So let's go back up to sum of 1. So what we're saying is, again, this was big O. If I was to do it in that notation, it was essentially just this. But again, the big O, that was going to be the objective nature of big O notation for this linear event. But the 1, as n gets larger and larger and larger, this number 1 falls off. So when n is 1 or 5 or 10, you'll see an impact of the 1. But even just getting to 100 and then 1,000, this 1 becomes meaningless. So we end up with a big O notation n. And again, this is not supposed to make a lot of sense to you just yet. It will as we get further down, when you can see the stuff in a graphical analysis. So I wanted to bring this idea again of describing limited behavior from an asymptotic analysis standpoint. So here I just created a function called big O with one argument n. And this is simply just returning 45 times n cubed plus 20 times n squared plus 19. And if I call big O with an n of 1, I'm just going to get 84. And if you wanted to do that math, you absolutely can. Just don't forget you have to do operations. So it's 1 cubed times 45, and then 1 squared times 20, and then plus the 19. And you're adding all that together. So if we just did 1 of the variable, we're going to get 84. So what happens if I do just 2? We automatically jump from 84 to 459. So what I wanted you to see is that just looking at these two here, all we did was change n by a factor of 1, correct? And yet our results substantially changed. But the point is that this 19, it had an effect here, even if from a percentage standpoint. When n is 1, 19 had an effect. But when n is just 2, the 19 is pretty much becoming meaningless. So this would not contribute to our computational intensive time because it's not really having any kind of an overall effect. It's not limiting how we're progressing in terms of scaling. So what happens if we go to a big O of 10? So now we're up to 47,000. So now looking back at our piece here, I'm going to get to the second. Going just from 1 to 2 to 10, the 19 we already know is pretty much out of the picture. 19 is not going to make a big difference here in terms of computational intensive requirements. So then the question is going to come down, which one of these is it? I'll tell you right now, you ignore the constants, never look at constant numbers. So what we're really focusing on is n cubed and n squared. And then we're pretty much saying which one of these is going to be the bottleneck, which one of these is the limiting factor for this particular function. Well, it can be seen that the 19 doesn't hold much weight anymore, and we came to that conclusion already. The 20n squared in this case is 2,000, so out of 47,000, if we took out 2,000, we're not that far off. If you do 45,000, if we get rid of the 19. So again, 45,000 and 47,000 is not that big of a difference. So we can pretty much conclude that the n squared is not going to be the limiting factor within this particular function. So then we have the constant 45 don't care about per se, but the n cubed I do. And with our n of 10, it's going to be 45,000. So 45,000 and 47,000 have much more of a percentage-based impact on its outcome of the performance of the calculation of that particular function. So in this function, this entire piece here, you would say this is essentially going to be your controlling big O. This is what's going to determine your scalability. This is what's going to determine your limiting factor. This is what's going to determine who's going to have the biggest bang for your buck within your function, and which is going to require the most computational time in your system. So this part of the algo that really has a lot to do with the final answer as the data scales. It's not going to be the 45 again. Here we have, it's not going to be the 45, but it's going to be the n cubed. So this algorithm has an order of n cubed. So it's a big O. Whoops a daisy. Let me put this in here. So this is going to be a big O. And we'll just keep it this way. That would be the order for this particular function. Now what I have here, this is just a big O complexity chart. We have horrible, bad, fair, good, and excellent. So what this is showing that these are different elements, and then we have the operations. So if your function has a big O of 1 or a big O log of n, which is still going to be quite linear, you can see that our performance here, as n grows, n's getting bigger, 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 and this is the operations, the amount of operations that be performed. You can see that we're in the excellent range here, excellent and good range for those particular big O's. But then once we start to get to, this is O with the function of n, which is very much like our original function that we did, sum of 1, you can see we're in a fair from a performance standpoint. As n grows, so too does the time, but the complexity of the nature that is not obscene. And then we start to get bad once we get to big O n log n, and then we're getting into the horrible territory when n is squared 2 to the exponent of n. Over here you would have n cubed. N cubed is even worse than 2 to the n in terms of operational performance. This is something you can memorize. I have 2 different charts here you can look at, you can go through. So for the big O, a big O of 1, that's called a constant, which is exactly what we'd have. This is going to be whatever. If it's a, big O is 10, then it's going to be 10. That's going to be the constant number. Log of n, logarithmic and linear. We saw that log of n and the constant and the O and linear, they're pretty fair in terms of as your elements grow, as your n grows, your operational computation intensive doesn't grow substantially. That it's still considered a valid function, a valid formula you're going to be using. And then we go n log linear. We're getting into that, what was that, fair? No, bad. So we left fair, we're in bad territory already, just because of the amount of computational intensive that is putting on the system, regardless of your system. And then we have n squared, n to the third, and then we have 2n in terms of quad, cubic, exponential. So this is just things you can start to memorize, and what you're going to be doing is this is what we're looking at when we're determining our function. Where does it fall in terms of the big O? This is a more broken down version of the big O, showing our 1 log of log n log n and so on and so forth going, and this to what their actual functional name is going to be called if you were ever describing it. What I have here, this code, I'm not going to go through per se. I'm just using this from demonstration purpose. But we're importing log, importing numpy, importing matplotlib. I'm going to have matplotlib in line, which you're going to see in a moment. Setting up runtime comparisons. So what we're doing is we're using numpy to create a line space 1 to 10, and then we're giving it different labels: constant, log, linear, quadratic, cubic, exponential. And then what we're telling it to do here is the actual calculations. Each one of these calculations is corresponding to its particular label. So therefore, this could have been done even like a dictionary if you were going to do key values. And then we're just setting up our figure size, and we're going to be plotting it. And then this is how we're actually going to go through the calculation piece. What I'm going to do is go through that, and here we go. So what this is just another graph version showing you that the n increases with the relative runtime on a particular system. So in this case, this is my system, and it's giving you a color code below that we're constant, log linear, quadratic, cubic, exponential. So again, you can see we're in good, better, worse, and then just asinine territory. So even with the n of 4, you can see the relative runtime performance. So here, when we're in constant and log, so we have constant log at 4, our relative runtime is, you could say that's like 1 and change. And then once we start to get up to linear, log linear, even with the n of 4, we're still under 10 for relative runtime. So it's not crazy. These guys can be somewhat grouped together. But now we're launching out of the territory here with quad, cubic, exponential. Even with the n of 4, we're hitting relative runtime substantially. And look, with an N of 4, we're looking to go off a relative runtime here, even for a cubic, and we're out of the ballpark. And what did we find for cubic was that's exactly what this big O notation was for this particular, it was cubic run. So its big O was cubic, so in terms of its relative performance, you could see with a small n, with an N of 1 and N of 2, we saw a substantial change. Then N of 10, it just skyrocketed. So we're here with an N of 10. You can see how the relative runtime, if we ever even get up to the cubic, it just rises at exponential. It rises at a cubic rate. So clearly, we want to choose algorithms to stay away from any exponential, quad, or cubic behavior. In terms of computational intensive, typically mathematics, and you're going to see this when we're doing machine learning and AI, and we will do exponential, quadratic, cubic behaviors, but we don't want to be doing them on large scales. So if we're going to be doing them, we want our n's to be relatively smaller. So if we keep our n small, we can keep our relative runtime in a manageable fashion. But again, this is exactly why if you're running certain neural networks on particular models on different PCs, why you can have runtimes that go hours, days into weeks, depending on your system, and why things like the GPU and its parallelism, why it has such a massive impact on decreasing the amount of time that we can run with ML, AI, and DL. And even something you're going to see soon coming out, which is the NVIDIA Volta. Well, it's already out. One of the biggest pieces of that is its ability with tensors. And when you have a GPU that is primarily focused on tensor mathematics and manipulation, you're going to find that the scaling of that is going to be astronomical, and the speed of that is going to be a heck of a lot faster than what we currently have, even with, say, the Titan XP running up with Pascal. So that's going to be it for today. Again, this was beginning of algorithms, and we start with a big O notation. So, and this information that we're doing now is not just for, like, say, for computer science, and it's not just for your own knowledge. All of this is, even if you start going to interviews for computer science, you're going to be dealing with functions or formulas that are going to be looking, where are they falling in this? Are they computationally intensive from a memory standpoint or from a time standpoint? How could you make them better? What could happen that could make them worse? And how can you make them functional in terms of what they're doing? Because again, you can code an incredible piece of code, but if it can't be run on 70% of systems in the world, then what good was the code? So you have to keep these things somewhat logical. Till next time.